Okay, so now we'll move on to the DC generators, right? So as the name suggests, a generator, it is going to generate current, right? It is going to generate current. So as we know, in thermal power plant, we are going to use a turbine, right? So how will we rotate this turbine? So we have a component structure called as a boiler in thermal power plants, right? So in boilers we burn coal to produce steam, high pressure steam. So this steam will be used to run a turbine. So we are providing external force and rotating the turbine, and this turbine is linked to the generator. Right? So now we will see how this turbine it is helping to generate electricity. Right? So again, this DC generator works on the principle of electromagnetic induction. So now we are going to induce current or generate current. So which Fleming's rule we have to apply? Fleming's right hand rule. So initially we are going to just take a rectangular shaped armature. So typically we will be having a cylindrical shaped armature inside a DC generator, but for our understanding we are going to take a rectangular shaped armature which is rotating inside a magnetic field. Okay. So we have a single turn loop. We have 4 points A, B, C and D, which is rotating clockwise in a uniform magnetic field. Right? So now when the armature is rotating, the magnetic flux which is linking the coil, which is both sides A, B and C, D, will change continuously. Right? So we'll see this using the diagram. Okay. So as you can see here, this is the initial condition, right? And the direction of rotation is clockwise. So just consider the current is moving inside near the point 5. So the current, it is going to be induced near the point 5. So let us say as it is rotating clockwise, the particular portion AB, it is going to be moving up, and the part DC, it is going to be moving down. So now just apply the Fleming's right hand rule for the part A and B. So it is moving up, right? So this is the right hand rule. So this is the direction of force. So it is moving upwards, right? And this is the magnetic field, and so the direction of induced current will be pointing inwards of the point 5. So nearby the point 5 you have a wire, right? So in that direction the current will be passing, and it will be coming out of the wire which is near to point 4. Right? So this is how you find the direction of the induced current. So now what will happen when it reaches the point 3? You will be getting the maximum current value, and again when the position of the armature changes, what you will do is the induced current will be reduced. So it will be gradually increasing, then reducing, and then gradually increasing. So the output of the DC generator will be AC. Right? So what output we need is DC. So what we are going to do is we are going to use a part called as a commutator. So I'll show you this, I'll explain this in a small video, right? So after that, so before that we can see the EMF equation of a DC generator. So the EMF of the DC generator is directly proportional to the number of poles, the total number of armature conductor, and it is inversely proportional to the number of parallel lines within the armature. So we can say as the number of the number of armature conductor increases, the EMF will be increased, as well as if the rotation, the RPM increases, the EMF is increased, right? So we'll see a small video and then get back to the DC generator.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions, a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC power sources.